Hello, in this video let's discuss second and third question of today's contest. You are given an integer array of length n where nums is the permutation of numbers in the range 0 to n minus 1. You may swap elements at I and j only if bitwise AND of the both numbers is equal to k. Return the maximum value of k such that array can be sorted in non-decreasing order using any number of swaps. If the number is already sorted, return 0. And the constants are n is up to 1 and it is given that it is surely a permutation of integers from 0 to n minus 1. So we know the original array which is given, and also we know the final array, right? Because the final should be from 0 to n, because 0 to n minus 1 which is sorted. So we already have the original array and we also have the final one which should be found. So we can surely get indices which are at wrong positions that needs to be flipped. So let's start from some cases. The first case is if all the values are correct indices, then no need to swap anything. So the answer is 0, because it is given that if it is already sorted, given 0, return 0. So we are returning 0. And in the case 2, let's assume that there are two indices where the values are swapped. That means only at those two indices the values are reverse, and other all the indices the values are correct. For example, if the original array is 0, 1, 3 to 4, and finally it should be 0, 1, 2, 3, 4. So which two are the indices that have the different value? It is 3 and 2. So for this, what will be the answer? It is 2 and 3. One of the possible answer is 2 and 3, right? Because if k is equal to directly is this, then we can surely swap these two and then we can get the answer. But what is the guarantee that this is the only value and this is the maximum k? Because it is given that we have to return the maximum k but not any valid k. So if this is the answer, why there is no maximum, no other value greater than this? That is the main question now. So let's take an example. So we have 2, 3, right? So 2 in bitwise is this and binary is this. 2 is this in binary and 3 is this in binary. So what is 2 and 3? It is 2, because when we AND this 2, it will become 0. So the bitwise AND is 2. So the k is 2 for now. So for example, why we are assuming that we are only swapping these two, and why not taking any some other array in the array which is already correct and use of this, and then why we are not increasing our answer, and why only are we doing 2 and 3? So for example, we are assuming that we are taking another number x in the array from 0 or 1 or 4. We are taking one of this and then we are trying to swap any of this with this number and then other number with this number. So it will go to the correct position. These two will be flipped accordingly. So what are the conditions then? It will be x and 2. So because we can swap two numbers if only bitwise AND is k for every pair that we are swapping, not individually. So for example, if k is equal to 3, then if we are swapping any two indices, the bitwise AND should be k. Not only first or last, but every two indices that we select, the bitwise AND should be k. So we are assuming that we have 3 and 2. We are swapping x and 3 first and then x and 2 first. So bitwise AND of both these should be equal to same, and that should be greater than 2. Why greater than 2? Because we are assuming that we are taking other element which gives the better answer than we got, that we achieved while swapping the two numbers directly without taking any other extra number help. So the new condition will be x and 2 is equal to x and 3. So only then we can swap, and then x and 2 should be greater than 2, so that we can get a contradiction that swapping the numbers which are directly in the wrong position are correct and there is no need to take other elements help. So is there any value satisfying this both? Obviously no, because it clearly says that x and 2 is greater than 2, which is wrong, because the number is 2 itself. How can a bitwise AND with other number can be greater than 2? Bitwise AND is surely reducing. So for example, if we are going on adding elements, the bitwise AND will stay same or it will reduce. So how can it increase? So x and 2 greater than 2, it means that we have 2 and there is some other element bitwising AND with that increase the original number itself. This is wrong. So we are sure that there is no other possible x which can give the answer greater than 2. So for this case, the answer is 2 only. And how is that achieved? It is simply the bitwise AND of two values that are in different positions. Let's take another example also. So even in this, we have 4 and 6 at different positions, and even now the bitwise AND is 4. So x and 4 is greater than 4. The same case we achieved before, like 2. So even this is not possible. So now we are sure that it is better to only think about the indices which are at wrong positions, but not any other element. Because for example, we have only A and B, right? A and B is the maximum possible undervalue that can be achieved by both A and B. If any other number is involved, the bitwise AND will be always less than the bitwise AND of these two. So we are sure that we have to think only about the indices which are at wrong positions. No need to think about any other indices as a third party. So now let's come to next case. So let's assume case 3. So in this, 4, 5, 6, 7 are at wrong positions. So 4, 5, 6, 7, these are the numbers in binary. And then let's think what can be our answer for this case. So for these 4 numbers, what are the possible cases that we can swap 2 numbers? It is 4C2 because you can take any 2 from this. So this is the first possibility, second, third, fourth, fifth and sixth. So now we discussed that, for example, we are swapping into this ing. So if we are able to swap these two, and if we swap many other elements, bitwise AND of each and every pair should be equal to k, not a single one. For every pair, it should be equal to k. So for same value of k, we have to select 2 out of 6 such that all are selected ones. So what I'm saying, for example, we have 4, 5, 6, 7 in different positions, right? So let's assume that we are having 7, 6, 5, 4. And we also discussed that it is better to swap internally the elements which are at wrong indices without taking any other extra index. So we have these 4. So firstly, we can swap 7 and 4. We can swap 7 and 4 and we can swap 5 and 6. So by this we can get the original one correctly. So we can select, we can do operation 2 times, right? Whether it can be 7, 5 or 6, 4, we can do operation twice. So from these are the 6 cases that can be achieved to make all correct positions. So for example, let's take 100, 101. We are swapping these both in the first place, in the first operation, and 110 and 111 in second operation. So if we are doing this, the bitwise AND of these both must be equal. What is the bitwise AND of this? It will be 4. And what is bitwise AND of this? It is 6. So we cannot do these both operations, even though this covers 4 different values, 4, 5, 6, 7. This is 4, this is 5, this is 6 and this is 7. So even if we are trying to form few pairs with bitwise and to be same, it is not coming here, right? These are 4 and 6, so we cannot swap these both. And now let's take some other case. And 100, these both, 100, 101, 101, 111. And now what is the bitwise AND of this? It is 4. What is bitwise AND of this? This is also 4. So now we are able to achieve a value k is equal to 4 such that we are swapping these two and both the bitwise AND is also equal to 4. So 4 is one of the possibility of answer. We are not sure that it is maximum answer possible till now. We are just assuming that we just got that 4 can be an answer. And now let's take other value. So 100, 111, 101, 110. And even in this, the bitwise AND is 4 for both. 4 and 7 is 4. 5 and 6 is also 4. So even now the answer is 4. So from this we are able to see that we saw all the pairs, right? We checked each and every possibility which are from these 4. So we flipped these two, then these two and these two and so on. And even then the answer is 4. So from this what can we understand? So the answer is simply 4 because we tried all the possibilities and finally we only got 4 as the answer. There is no any other possibility. So from this we can understand that the answer is 4. And why this is 4? If we observe, it is simply the bitwise AND of all these. It is bitwise AND of all these. So, but why this is the maximum answer possible? Bitwise AND of all the values is possibility, but why is this the maximum answer possible ever? So let's take other example. Let's assume that these 5 are the indices that are at different, these are at wrong positions, and all other values are at same. So what is the bitwise AND of all these? It will be 100 because only at this bit all the indices are 1 and at any other bit there is at least 0, there is at least 10 and at least 10, at least 1. So the bitwise AND of all the other indices is 0. So the final bitwise AND of all these is 1000, which is 8. So now we are assuming that the answer is 8 also. Now let's think, is there any possibility that there can be an answer which is greater than 8? So for example, we are 8 in binary is 100. So what bitwise and is 8. So what it means? It means that at the other indices where bit is 0, we can have 1 or we cannot have 1. So if the bitwise and of few numbers is 1, what it means? Every bit at every numbers this bit is 1. Only then the bitwise and is 1. But if a bitwise and at some bit is 0, then it means that there is at least 1 0 and there may be at least 1 1. 0 is a must, or at least 1 1 should be there. So ones are optional and zeros should be there. So from this we can understand that given any numbers, we can partition those into every two numbers such that the bitwise and is 8. Right? Because for example, in this example, right, we got all this. So we are able to achieve some operations, some many operations using these four numbers such that the bitwise and is 4. So even we unable to got the answer using using the first one, which is 100 101 and 110 111. So by these both we did not get the answer because the bitwise and by here is 4, the bitwise and due to this is 6. So we are unable to get by this, but there are many other possibilities where we got the answer as 4. So from this, by taking many examples, we can understand that given many numbers, we can partition them into two numbers such that every bitwise and of those both is the bitwise and of the whole subset. So from this, we are sure that it is the maximum answer possible. So hope you got this. If you have any doubts, comment below. Let's discuss the third one. You are given two integers arrays value and limit both of length n. Two initially all are inactive. To activate an inactive element at index I, the number of active elements must be strictly less than limit of I. And when we are activating a number at index I, then add the value at this index to final answer. And then after each activation, if the number of active elements become x, all elements with limit of j less than or equal to x become permanently inactive, even if they are already active. Return the maximum total answer that we can get. The constraints are n is up to 1if and the values are up to 1if and the limit is up to n. So let's check the code of before one. It is simply we are traversing through 0 to 1, and if it is not equal to index, that means it is at the wrong position. So if it is at the wrong position, check if this is the first value. So if this is the first value, then answer is equal to v of I, else bitwise and finally return 0 if answer is -1 or return answer. We did not check the case where there is one different element. Why is that? Because how is it possible? There can be only even number of numbers which are at wrong position. So only that we discussed regarding 0 to 4 and so on. And now coming to the next one. So the question says that let's assume that inactive elements are bad, active elements are good. So activate bad index I if count of good is less than limit of I. This is what it is given. And if we are activating index I, add v of I to answer. And then after activation, make all the indices with limit of I less than count of good as bad elements. So by making sure of all these, we have to return the maximum answer. So let's think about limit of I first. So for example, limit of I starts from 1 and ends at 1 if I. So let's start from the first value. Let's start from the least value of limit I, which is 1, because it cannot be 0. So we can start from ending or we can start from beginning also. So let's start from 1 if I, from the last one. So for example, we are at 1 if I, right? And we have some elements with limit as 1 if I. For example, let's assume that 4 5. We have values 4 and 5 with limit as 1 if I. For example, we are making this as active. So if we are making this active, it is given that after activating, we have to check whether limit is less than the count of good as bad. So for example, if we are coming from back, we can come from front or we can come from back. So let's check a few cases and think about the answer. For example, limit of j is equal to 1. Let's assume that we are at first and we are thinking about the values with limit as 1 and then limit as 2 and then limit as 3. So coming to 1. So let's start with 2. For example, no elements are activated till now. So the answer is 0. The count of good is also 0. Count of bad is also 0. And let's start from this. So we came to 2. So we are coming to 2. Let's check if any of the conditions are violated. So limit of I is 1 because we started from 1. Activate bad one at I if count of the good is less than 1. The count of good till now is 0. So this condition is satisfied. So we can activate this one. So now the answer will be 2 and the activated is 2 and 2 is activated. So we added 2 to answer. And what is the count of good for now? It is 1 because we activated 2. Now let's come to 3. Now coming to 3, and it is also given that after activation, make all the indices with limit of I less than or equal to good as bad. Less than or equal to, so less than or equal to good as bad. So after activating the 2, the count of good became 1. So now we have to make all the elements as bad where limit of I is less than or equal to 1. So it means that we can't make 3 active or 5 active because it is given that after activating we have to inactivate all the elements with limit of I less than or equal to count of good. So after activating 2, the count of good is 1. So we cannot make 3 active or 5 active. We lost these 2. So the answer for 1 is only 2. And now come to 2. So let's think of 2 after. But is this the correct one that we are thinking with respect to 1? For example, we have 2, 3, 5, right? What if we have taken the maximum element in this? Then it would be great, right? Because we have selected 5. So the answer is 5 now. The count of good is 1. After activating, we have to make all the elements inactive with limit of I less than or equal to 1. So now we cannot activate this. We cannot activate this as well. And we cannot activate this because it's already activated. And the answer is 5. And the activated count is 0 because we made all these as inactive. So answer is 2 better or answer is 5, which is better? Obviously answer is 5 is better because it is higher. So from this we got that for value of limit 1, the highest value index is the one that we can select for activating. And then let's come to 2. So when coming to 2, the count, what is the answer? Answer is 5. What is count of good elements? It is 0 because we inactivated the elements. And what is the count of bad? It is 3 because 2, 3, 5 are inactive now. And then coming to 2. So let's start from 2. So we selected 2. So the answer became 7 and the count of good became 1. And then we made these both changes, and after activation make all the indices with limit of I less than or equal to good as bad. So the good is 1 now. So we have to inactive the elements with value less than or equal to 1. But these are already inactivated bad, right? Because these are already inactivated in the past operations when we are thinking with respect to 1. So we can still make few operations on 2. Why? Because we should activate only the elements with limit less than or equal to 1. But at the present situation, we are at the indices where the limit is 2. So we can still continue operations doing on 2. So let's come to 3. And we activated 3 also. So plus 3 and then plus 1. So the count of good elements became 2 now. And now we have to inactivate all elements with limit less than or equal to 2. So what it means? So now we cannot make any other values active if the limit is 2. So we are stopped here. So we selected only 2 and we selected only 3. And now we have to make all the elements with index 2 with limit 2 as inactive. Why? Because it is given that after every activation we have to make inactive elements with limit less than or equal to 2. So after selecting 2 elements of limit 2, we use the limit. We cannot make any other operations on limit 2. So from this we got that we have to select highest 2 values of these, right? So instead of selecting 2, 3, what if I have selected 4, 5? Even if I have selected 4, 5, the answer would be incremented by 9. And after doing both, we reach the same situation where we have to make inactive elements of all elements less than or equal to limit 2 which is same as is arcade 2 3. So from this we got that if we are dealing with respect to index with respect to limit 1, it is better to activate the highest value of I with limit 1, so that all other will not be activated according to third condition, and we got the maximum value when we are thinking with respect to limit 1 and even with 2. So for example, we have many values, it is obviously better to take only two highest values of this, so that after making these two, the count of good will become 2, so we will inactivate all these both, all these. So the answer is incremented by the maximum value because we are selecting two highest values. And for limit 3, it is better to take highest 3 values and so on. So from this it is very easy to understand. So we can use a map to store the values of the first array if the limit of I is y. And similarly for 2 we will add the vector a map and similarly all. And then we can sort all these, and then for a limit of I we can start from back. We can take maximum limit of I values. For 1 the highest value, for 2 highest 2 values if there are there, or for 3 for highest 3 values if there are there, and so on. And similarly return the answer. So highest of all values among all these. So let's check the code. So we are using a map to store. We are pushing L of I with vector of I, with the value of I, and then answer is 0, and then traverse the whole map and sort these all, and then we can select only p dot first values, which is limit. So we can take minimum of these both. For example, we are thinking with respect to limit 3, but what if there are only two elements? We can select these both. If there are more than or equal to 3, then we will select top 3. So what is the number of indices that we can select? It is simply the minimum of vector size and then the limit. So minimum of the vector of size and then limit, and then add all this to the answer and simply return the answer. So if you have any doubts, comment below. See you in the next video.